You see triangles everywhere, right? But have you ever stopped to think about the secrets they might be hiding? Well, it turns out this simple shape holds the key to solving some really complex problems, everything from finding the perfect meeting spot to even uncovering ancient ruins. So, let's dive in and unlock the secret centers of triangles.
So let's start with a puzzle. Imagine you and two of your friends want to meet up somewhere, but you want to be fair. You want to find one single spot that's the exact same walking distance from each of your houses. I mean, you could guess, right? But there's a perfect mathematical way to find that one spot. So how would you do it?
Well, the answer to our puzzle lies in these special points that are hidden inside every single triangle. They're called points of concurrency, which is just a fancy way of saying it's where specific lines cross. And each one of these points has a unique, almost magical property. To solve this whole friend's house problem, we first need to pop open our geometric toolkit. And the first tool we're going to grab is something called the perpendicular bisector. Okay, the name sounds a little intimidating, but it actually does exactly what it says. It bisects a line segment, which means it cuts it perfectly in half. And it does that at a 90-degree angle, which is what makes it perpendicular. Now, here's the key thing. Any point you pick on this bisector, any point at all, is going to be the exact same distance from both ends of that original line. So here's where the magic happens. What if we draw a perpendicular bisector for all three sides of our triangle? You might think they'd cross all over the place, but no, they all meet at one single amazing point. This point of concurrency is our very first secret center. We call it the circumcenter. And boom, just like that, we've solved our puzzle. The circumcenter is the one and only spot that is the exact same distance from all three corners or vertices of the triangle. It's the mathematically perfect meeting place for you and your friends. And this isn't just a party trick for planning hangouts. Archaeologists use this exact method. Seriously, if they find three stones that they think were part of an ancient stone circle, they can treat those stones as the corners of a triangle, find the circumcenter, and that tells them exactly where to dig for, say, a central fire pit. Pretty cool, right? Okay, so we've found a point that's the same distance from the corners. But what if we have a totally different problem? What if you need to find a point that's the same distance from the sides, the edges of the triangle? For this job, we need a different tool from our kit, the angle bisector. This is just a line that starts at a corner and slices the angle into two perfectly equal smaller angles. And the key property here? Any point on an angle bisector is the exact same distance from the two sides that form that angle. And you can probably guess what's coming next, right? Just like before, if you draw the angle bisectors for all three corners of a triangle, yep, they also meet at a single point. This one is called the incenter, and this is the point that is perfectly equidistant from all three sides of the triangle. So let's put these two side by side, because this is really important. The crucial thing is knowing which center you need for which job. If you need to be an equal distance from the corners, like your friends' houses, you want the circumcenter. But if you need to be an equal distance from the sides, like if you're trying to place the biggest possible circular fountain in a triangular garden, you're looking for the incenter. All right, let's move on to our next secret center. This one is less about distance and more about, physics and balance. Every single triangle has a perfect center of gravity, a single point where you could literally balance it on the tip of a pencil. So how do we find this magical balance point? We need our third tool, and this one's called the median. And a median is super simple. It's just a line that connects a corner to the exact middle of the opposite side. That's it. And by now, you know the drill. When you draw all three medians of a triangle, what happens? Of course, they all intersect at one single point. We call this one the centroid. And this is the triangle's true center of mass, its center of gravity. Think about it like this. If you had a triangular serving tray like this one, the centroid is the exact spot where you could put your hand underneath to hold it, and it would stay perfectly balanced. It wouldn't tip at all. So yeah, it is literally the perfect place to put the bowl of pretzels. Okay, so we found these amazing secret centers, but there are even more fundamental secrets to talk about. Like, what actually makes a triangle a triangle? It turns out you can't just take any three lines and stick them together. There's a rule. Let's just take a look. Say you have these three line segments right here. Can you connect them end to end and form a triangle? Yeah, sure. Looks like it works just fine. But what about this set? You've got one really long side and two much shorter sides. No matter how you try to arrange them, the two short sides just can't reach each other to close the shape. So what's the deal? Why does one set work and the other one doesn't? The answer is a really simple but incredibly powerful rule called the triangle inequality theorem. All it says is that for any triangle to exist, the lengths of any two sides added together must be longer than the third side. If they aren't, like in that last example, well, they just won't connect. You don't have a triangle. And for our final secret, let's look at the relationship between a triangle's angles and its side lengths. They aren't independent of each other. They're connected in a really intuitive way. Just think of a swinging gate. The gate itself and the fence post it's attached to, those have fixed lengths, right? They don't change. But as you swing the gate open, the angle at the hinge gets bigger. And look, the distance between the edge of the gate and the far post also gets bigger. It's a direct relationship. What you just saw, that is the hinge theorem in action. It just says that if you have two triangles with two matching side lengths, the triangle that has the bigger angle hinged between those sides will always have a longer third side. It's really that simple. The bigger the angle, the longer the opposite side. So, you see, from finding a fair meeting spot, to balancing a tray, to understanding the fundamental rules of construction, these principles are everywhere. They're not just some abstract ideas in a textbook. They're the invisible code that actually governs the structure of the world all around us. Now that you know about these secret centers and these hidden rules, you're going to start seeing triangles differently. They're not just shapes anymore. They're puzzles that have these elegant answers built right into them. So the only question left is, where are you going to spot one next?